Okay, so it's my pleasure to introduce Professor Alejandro Maass. He's going to speak about variations on recurrence.
Okay, thank you very much. So, thank you to Christian who invited me last year to come here. It's always a pleasure to be in Brazil and to see my French friends here, and Brazilian friends, of course. Yes. So maybe I will change a little bit the title to be more precise. So first, this is a joint work with Bernard Host and Brian Accra. Maybe the correct title is something like some results related to the Katnelson conjecture, yes, on recurrence set. So and this is what I will present, is not variation, but this is a problem where we arrive just studying what we study since a moment with them about topological nil factors of a system. Yes, so the title is something like about some results related to Katz-Nelson conjecture. So before stating his conjecture or his question, maybe, let's define something that's very natural in ergodic theory, a recurrence set. So first, my setting is always topological, even if this can be defined and is maybe first defined measure theoretical system in measurable dynamics. So my setting will be without measures, so will be a minimal topological system. So this means for me this is a compact metric space, and T will be a homeomorphism. So in this setting, you can, so we know we have recurrence since you have a minimal system. If you take any open set, we know that, so if I take U an open, non-empty open set in X, we know that there's some times where U inter T minus and U is not empty. Yes, so there are some times where you go from U to U, so classical recurrence in a minimal system. So you can ask if you, for some subsets of n, this is also true. Yes, so you define, you say that R, a subset of positive integers, is a recurrence set. Maybe I will add here a simple recurrence set. If for any minimal system, minimal dynamical system, for any U as before, you can take some time in this set such that you can go from U to U in this time. Yes, so, and there are many examples of recurrence sets. So n, of course, the difference of an infinite set of integer, this is Furstenberg example, I think, the shifted primes, and many examples that I'm not very expert on R, and what I will present try to avoid really R, because the recurrence sets are very, let's say, of different nature. You have very dense, if I can say that, recurrence set, but also you have very sparse recurrence set. So in this sense, maybe it's not a good notion, but it has been studied for a long time, and there is this conjecture by Katz-Nelson I will present now. So if the Katz-Nelson conjecture is not related to discover which are the good recurrent set, it's more related to have recurrent sets maybe for not all minimal system, but for some class, and try to see if you can extend this recurrent set to a bigger class. Yes? In his case, the simplest class you consider in ergodic theory are rotations in compact abelian groups. Yes? So you can define the notion of, we said that R is recurrent for a family F of minimal dynamical systems if for any let's say, xt in f, you have the same result. Yes, so you have a restricted notion of recurrence. And when f is are rotations on compact abelian groups, we put a name to this kind of set. We said that we say that R is Born recurrent. And the question or the conjecture, I don't know, maybe a question of Kastnelson was the following. So the question or conjecture is the following: if R is Born recurrent, then is recurrent. And everything is topological, yes? So that means that if I have a subset of the integers such that you can have recurrence on it for rotations you have for any minimal systems, yes? And of course you can extend this question. I will extend just now to have the definition. You can also speak about multiple recurrence at the same time and as the following: if you are multiple recurrent for some class, can you extend to a bigger class? Yes, and which classes are natural for that? I don't know what is the motivation of this question, which were the computation of Kastnelson, so I cannot tell you. So we try to compute and see where we can arrive, and I will show this in a minute. Before I will write what I said. So if you take an L, an integer, so bigger or equal to 1, so you can extend the notion of recurrent set to, let's say, a recurrent set, saying that for any set R, if for any minimal system, and U, as before, open, non-empty, you can take some time here in R such that you have multiple return times on this kind of arithmetic progression of length L. Yes, so you have L consecutive returns to U with step n. So you can ask the same kind of question. You can define the relative L recurrent set with respect to a family, as before. And you can ask if you can, but here there is not a Kastnelson conjecture, but you can ask if R is L recurrent for F. Does it imply that R is L recurrent for some family containing F? Yes, a bigger class. Yes, what are the candidates? In fact, this was after we looked to examples that we conjecture and we proved something for L recurrence. The same history with R, L recurrent R's and recurrent R's are sets of different kind. Yes, and they appear in many situations. I will show you one from some recent results by, just to show you that they can appear in many different ways, but in particular in dynamical systems, they are intrinsic to the dynamics. There are some recent results by Wang, Song, and Ye, where you construct L recurrent or single recurrent set just by sending regionally proximal points to other regionally proximal points. In fact, this is a very general way to construct them, and I will make a picture. There is, I will not go into detail for the moment, but this is one of the motivations why we went into this problem. But if you have your minimal system, you have some factors I will write in this way. I will call set D. That we call this the D-step topological nil factor. When D is equal to 1, this is the maximal equicontinuous factor or the topological Kronecker factor associated to X. And so you have fibers over these factors. This fiber is produced by some equivalence relation. And if you take an open set around Y, and you see the entrance times of X to this open set, those times forms a D recurrent set. Yes, this is a very general result. So that means that you have a lot of L recurrent sets coming just from dynamics. Yes? So if I take an XU, so the times such that Tn of X belongs to U is a D recurrent set. Moreover, if this system X is a D plus 1 nil system, so you will create something that is D recurrent but is not D plus 1 recurrent. Yes, so you have many examples to show that this notion here is different for each L. Of course, before there exist some examples about that. Yes, but this is a way to prove, very abstract way to prove. So, okay, so when you do topological dynamics and you try to go from the rotation on a compact abelian group to any system, minimal system, so a naive but effective sometimes way to think is just try to see if you can pass your property through extensions. Yes, we know there's a general structure theorem that said that you can essentially construct any minimal system from the maximal equicontinuous factor or from a point, taking isometric and proximal extensions. Yes, so you ask if you can pass your property through those properties, so those extensions, sorry. So the first, so some steps to try to prove something. And I suppose that Kasnelson, he thought about that too. So try to see if you can pass your recurrent set from a rotation to a proximal extension. And with proximal extensions, you are happy because it's very simple. Yes? You have, suppose here you have a minimal system. I will call set T. It's a minimal topological system. And R is a Bohr, is recurrent, I will say, here. And here I have another system, X, that is a proximal extension of the base. And I want to see if R, I can lift R to xt. Proximal extension means that if I am in the fiber, if I have a point, 2 points in the fiber of any point here in the base, I know there is some, let's say, I will write in subsequence, some subsequence of X going to X prime. Yes, this is a way to say, and T and I X primes go to X prime too. So in fact, you have any 2 points here, they will converge by subsequence to the same point. Yes. So how you proceed? If you are recurrent, so there exists some point in the base, and this was proved in several papers before. This property with the open set can be translated in the fact that you have a lot of points here, such that you have a real point-wise recurrence to him. Yes, this a G delta set, in fact. So you have a point here, we'll call Y0, where you come back to him through a subsequence. So that means that if I take a point, any point in the fiber, via another subsequence, I can make it converge somewhere. I will call X1. And since this is a proximal extension, I know that I can go from X1 to very close to X0, and from X0 to itself very close by some m, depending on the very close I'm choosing. Yes? So that means that the point Tm of x0 is close to x0, and when I make Tm plus Ni of x0, I am very close to x0, just by continuity. So I have proved that there is a point that is very close to x0 that after Ni, and Ni I can choose this in the R, sorry, in the recurrent set I was working. So it's a recurrent time for this point in the file. In fact, this is very fast, but I just want to say that it's a very simple argument to show this, and you can repeat not for single recurrence, but for L recurrence. So same argument works for L recurrence. So proximal extensions are okay. So you have, if you have any, for example, almost one-to-one extension of some rotation, your recurrence set in the base will be lived. So Sturmian sequences, I don't know, Toplitt sequences, many sequences that we handle all the time. Yes? But the second kind of extension we want to understand are the distal, I will say distal extensions, or isometric extensions. It's not a synonymous word I will put here, or let's say group extensions. I want to say that extension that will not collapse the fibers, but they will keep points at a positive distance all the time. Yes? And this is the big problem, in fact. This is the problem. So when you speak about distal system, you have the first distal system in your mind that I will write here. So you make a computation, and you try to see if there is some theorem related to it. So to summarize, now I want to prove that distal systems, they verify the Kastelson conjecture. This is the question. So you take an example. In fact, my talk will be just computation of 3 very simple examples. So this is the very classical distal system that is an affine nil system too. So in the two torus, you write this system. This is a distal system. It's an extension of a rotation alpha. I will take irrational. Of an irrational rotation in the torus. So you want to prove in this example that the conjecture is true. So let's prove here the conjecture. So you believe me, if this is T, you can compute T to the n. This is just matrix computations, and this is an x plus something like this. So what do you have? You have R, that is a recurrent set in the base that we want to lift. So what that means essentially that since this is a recurrent set in the base, suppose this is x is 0. If I want to come back very close to a neighborhood of 0, I have a point in this neighborhood that will come through R. Yes? But since this is an isometry, I can move a little bit this point in the base, and I will have the same property. Yes? Because it's an isometry. So suppose that if in the base I take U, and I have a point here coming back through a time in R. So I want to move this in plus or minus epsilon. I will have the same property. Maybe U will be larger. Yes, I will not make all the computation, but this is not a problem. Yes, so I have points in the base that come back through R with big n's in R, maybe, to a fixed neighborhood. And I know I can move a little bit. And I will still have the same property in the base. So since I have this little movement, and n can be large, if the movement is epsilon, I know that if n is large, n times the interval of length epsilon is surjective on the fiber, yes, on the torques. Since this is surjective, that means that I can choose an x here going wherever I want in the second coordinate. And this proves that I can lift, yes, the recurrence set. So, so here the argument is that if n epsilon is fixed and n is enough large, then multiplication by n, let's say multiplication by n in a little interval minus epsilon epsilon is onto. Yes? So I repeat, though, this will means that I have a point coming back to a neighborhood. I can move a little bit in such a way that I will adjust the second coordinate as I want. So I will come back wherever I want in the fiber. Yes? So this we call dilation property. So this is true in this example. Yes? So conjecture. This is very naive conjecture, by the way, in the first. This is true for any nil system. Okay, why from this example? Of course, this is no sense, but yeah. This is a two-step nil system. Yes, this is a rotation. This is an affine nil system, and this is true. So what you think is that in the nil system you have some polynomials equations you will you have to solve, and you make the example with the next in the next step, and you more or less are convinced that always you can do the same, but you need to implement that. Yes. So the conjecture is that if R is Bohr recurrent, then R is recurrent for. I will show you what is a nil system. If you don't know. Nil system in the most general way, so inverse limits of nil system of some step. Yes? And so this is the first conjecture. In fact, it's a theorem now. Okay, so let me do another example. Maybe continue with the same. If you want to extend to any nil system, maybe you need another technique. And so I will go to Marius techniques. So no Gaussians, but spectral theory. Yes. So suppose you want to prove this in general. In fact, you just compute using the measure. So you suppose you have your system, xt, with some measure. So you can project continuously, in fact, if I am a nil system, to the Kronecker factor, where this is the hard measure. So you can project this system there. I will take an open set, my open set here, and I will try to compute the measure of u intersection t minus n of u for some n. And I will have my recurrence set here, Bohr. In fact, doing this computation, we discover it could be much easier, but it only works for some cases. So you want to compute this measure, so you integrate. So you just put as an integral way. You put in this way. And to use, let's say, the spectral measure, we will project this map to the Kronecker factor. Yes, this is what we'll do first. So let's call f the indicator function minus the projection to the Kronecker factor that I will see either in the base or in the space. Yes, I will project on the sigma algebra generated by this Kronecker factor, and I will call this conditional expectation g. So the indicator is f plus g. So when you replace here you see that the f is projected orthogonal to this factor. Yes, so that means that when you multiply, you can separate this integral in f on one side plus g in the other side. Now I will write g, in fact, in the base, just because it's more comfortable for the remaining. So you have two parts, the first and the second. Of course, two parts. The first. So this part is a function that projects orthogonal to the Kronecker factor. And in a spectral theory, that means, for example, if the spectral measure associated to f has an absolutely continuous part, then this limit goes to 0 with n. Yes? In general, this will go to 0 through a subsequence. Yes? This is a general result. But in some cases, this goes to 0 with n. Yes? And this is just a spectral property. So we need now to control this part of the g part. And but this part is just, you use the isometry in L2 that is induced by t. So this part, let's say star, so is, I will say, I will subtract g here, and I will add. So this will be bigger or equal than the L2 norm to the square of g plus, or minus, in fact, using Cauchy-Schwarz, something like g square L2, or without this, of the difference of g Sn Tn minus g. So if I take n in such a way that here is a rotation plus alpha, in fact. Here I am in a rotation part. So if n is such that n alpha is close to 0, then this term is little. It's just the isometry in the L2. This is general result. Since g was an indicator function, this is lower than 1. And this is the measure of u to the square. So this term is always little. So the result depends on the spectral part, I will say, this part here. So if for f, let's say if the system for any f such that this is 0, the spectral part is absolutely continuous with respect to Lebesgue, this goes to 0 when n goes to infinity. So, and this is true for nil systems where the associated group is connected. Or when the step of the group is 2. I will say after the definition, I'm sorry. But so for many cases, this is true. In the connected case, this was proved by, I don't know, Oslander, Green, and Hahn in the 60s, 70s. And for S equal 2 without hypothesis, we wrote a proof in some appendix of an article some years ago. We didn't write for all the S because it was too hard. But it seems that this result is general for any nil system independent of the connectedness. Yes? So this is true. So that means that if you take a small or little, something like the measure of u divided by 2 to the square, you get at the end that this is positive. Yeah? So a simple computation also gives you the same kind of results, extending a recurrence set from a rotation. Yes. Okay, but the problem is that not all nil systems are of this type. Yes. Let me write a definition for those. In fact, I wanted that Sebastian define what a nil system is, but he didn't. The previous talk. So the definition is that you take G is an nilpotent Lie group, and you have gamma a co-compact subgroup, and you consider X equal to G over gamma, and T of a point that I will write as a coset is just tau G gamma for tau, a fixed element. So it's a rotation in this nilpotent group. And if GS plus 1 is the identity, so in the series of commutators, we said that X is S-step Nil system. Where, so G1 is G, G2 is the commutator, the G with G1, etc. Yes? So what I was saying here is that if S is equal to 2, like in the example, this property is always true. So we have the conjecture for the two-step Nil systems. And if G is connected, this is true also. So it's also true. But we have a combinatorial proof. Maybe not combinatorial. We have a topological proof for any S for the conjecture. Our conjecture, I say, for the question. For the second conjecture, yes. So that means that if you have R is a subset of the integers, that is a recurrent set for the rotations on a compact abelian group, then it is also a recurrent set for any Nil system. So how far we are from the conjecture? Of course, very far, but you have much more systems that can go inside the set of minimal systems, because we have the following picture. We have Xt. It has its maximal distal system here. You have the maximal topological Kronecker here on the other side. And in the middle, you have many, the second step maximal Nil system, the third, etc., until something that we call the set infinity that combine all these Nil systems in one. Yes? So if you are an almost one-to-one extension of this kind of systems, you verify the Kasnelson conjecture. Yes? Which system verifies this is very abstract. There is a theorem we proved with Ye, Sebastian Donoso, and Song. Said that a system is an almost one-to-one extension of the Nil part if only if you have what we call the independence property. This is a property that was defined by Ivanik several years ago and was adapted to this context. Yes, but if you have a lot of independence, you are in this class. So for those minimal systems, it's true. Okay, so this is for the single recurrence. So what we can say for the multiple recurrence. So I will take an example. I want to generate a conjecture. So I will take an example. So the example is the following. I will go to the next Furstenberg, I don't know if we call it like this, Furstenberg affine systems. So the second example is take x, y, z and take the basis of rotation. The first two coordinates produce a two-step Nil system, and the last one constitute globally a three-step Nil system. Yes? And what I will try to prove, in fact, what I will show you in the example is that if you are two recurrent for the first two coordinates, you can go to the next. So in fact, the picture that we have in mind is the following. If you draw here you draw the step of the Nil system, and now I am concentrated on Nil systems. If here you draw the step, and here you put the recurrence, the degree of recurrence, So we just proved that if you are one recurrent for one step nil system, so for rotations, then you can go to the next, to this arrow. So the point now is the following. Suppose you are two recurrent for someone. Can we go to the next step? So here, okay, here by the techniques by Wang, Song, and Ye, we know that here we have some counterexamples. So the point is to prove this first arrow. If you have, in a second step, in a two-step nil system, you have a two recurrent set. Can we say it is also a two recurrent set for three steps nil system? Yes? So what we want to prove is this line here. And of course, if you have some L here and you go to the diagonal somewhere here, L, we want to go this way. In fact, I will not have time, but all the other arrows in this direction are false, and this can be proved using the Wang-Song-Ye technique. Yes? So let's prove this first arrow here in an example. Yes? So again, we need to see if there is some possibility to be true. So this is theorem 1. This will be theorem 2. Okay, so again, this is my base. And in this base, I have a R is a two recurrent set. That means that you are recurrent for two times for n and 2n. Yes? And I want to prove that some time that allows you to come back in the base also allows you to come back in the complete system or in the fiber. So again, if this is t, this is t to the n. You can write as before, is something like this. I have to believe myself, I suppose it's something like this. Plus a polynomial of degree 3 times alpha or something like that. Yes? So you have a time n, and some point, let's say xy, coming back very close to itself for this time n in R. Yes? You have n in R, and you come back through n and 2n very close here. So first you have to see if you can move a little bit x and y. Yes? How far you can move x and y to be close again. So in x, just to be very extreme, I will say that in x I will move epsilon over n, and in y I can move epsilon. Yes? If I move x in epsilon over n, I will move globally epsilon, in y epsilon. So here will be just epsilon in both coordinates. Yes? So I have this march, this, I don't know, degrees of freedom for x and y. Yes? So x can move by epsilon over n, and y can move by epsilon. And I will preserve, if you want, the recursion in the base. In the base is n and 2n, but when I change here by 2n, it's not a problem. Yes? I will move by epsilon. So now I want to see if moving x and y a little bit in this range, if I can go everywhere with this expression in the fiber. Yes? This will mean that I will come back, yes, to any open set I put in this coordinate. So you can forget about set. You will try to solve the following equation. You will write something like n minus 1 x plus ny. I will say very close to some value. And you want to also to, I will write in the other way, sorry. I will put ny as was before. So if I repeat the argument I did for the classical distal system, I am two recurrent in the base, so I move by n and 2n for some n in R. big as I want. I can move the n if I want. The epsilon is fixed on the other side. So I want to see if in the fiber, when I move through n and 2n's, I can be close to any value I want. This is enough to prove the recurrence in the fiber. So you reduce this system, and you get something like ny plus n minus 1 x some value, multiplying by 2, subtracting, and here you get n squared x close to some value. Different values, of course. So this system is equivalent to this system. And here I go back to my little movements. So I know that x can move by epsilon over n. So when I multiply 1 times by n, I get an interval of length epsilon. And when I multiply by n is big, to this little interval of length epsilon, I get the complete fiber. Yes? I take my x, because I can solve this equation in the interval epsilon over n with these little movements. I replace my x here, and now I have ny equal to some value and xy equal to some value when y can move in this little interval epsilon is also subjective to the fiber, so this system can be solved. Yeah? So when you repeat in more examples, you are convinced this is true. So this is theorem 2. So theorem 2 is the following. It says that so in the affine case is ourself. We're more lazy than Wembo. This is Wembo-san, and this is Maass. Here we prove that if you are R is S recurrent for a step, then you are S recurrent for, let's say, T step for any T bigger or equal than S, and this is the same. So if you are in the affine case, are all examples that looks like this one. In the general case, it's just any step, any rotation in a step nil system. And the proof here is really a generalization of what we did in one dimension. But you need to control many, many commutators, and this is for a fresh PhD students who did Wembo-san in Northwestern. Okay, so the table here is true. So you have counterexamples before the diagonal and after the, let's say, the extended Catanelson conjecture is true in this family of S-step nil systems. Here also you have arrows that are here is false and here is true, etc. And these arrows are, here is the Wang-Song-Ye theory that I will not tell you here. So you have a complete picture in the, of the recurrence sets inside the S-step nil system. Just to finish, let's put another question. This is true in the nil system, but it's no sense that it's true only in nil systems. So one argument is this computation here. When you have, for example, any system with the same property, you will get the same conclusion. So it's not only restricted to nil systems. So of course, there is a bigger class. So one example where this is true, so non-necessarily nil systems, where this is true, is when you take x, y, some cocycle extensions, y plus, making this continuous, yes? So if you take some cocycle here to make this continuous, when the degree of phi is different from 0, this is so the conjecture is true. You can make by hand, by the way. So you can, I don't know. There are many examples where you can compute again and prove that if you have a recurrence set for the base, you can leave it here. There are many symbolic systems that you get by coding this kind of things. There are some examples by Arnaud Mauduit in some affine systems. You code some polynomial sequences, so sequences of polynomial complexities where you have this property, etc. So there are many, many systems where this is true. And of course, the nil systems is a little class, maybe very natural to be associated with the rotations, but still very little. Okay, thank you very much.
Questions?